Hey there. In this video, we're continuing our discussion of conditional distributions, and we're going to see that if we don't require that one of the random variables take a constant value, in other words, if we don't require that x be x0 or y be y0, then conditional probability density functions can actually be functions of two variables, and we're going to see that in example 7.7.5. So let x and y be as in example 7.7.3, and this was their density function. We are now asked to find the conditional density for x given that y is equal to y of x given that y is equal to y. Notice that this is for a variable value of y and not a constant value of y. So we have to remember how to find a conditional distribution, and we want to take the joint density function and divide it by one of the marginals, and the marginal that we want is the marginal of y. So that means we need to calculate this marginal first, which means that we need to have a look at the support that we're going to be integrating over. So let's draw ourselves that support, and x goes from 0 to 2, y goes from 1/2 x to x, and so we end up with this triangular region here where this is the point 2, 1, and this is the point 2, 2. So this is the function y is 1/2 x, and this is y is equal to x. Now, we are going to be integrating out the x to find the marginal. So f sub y of y is the integral from minus infinity to infinity of the joint density function dx. So we're integrating out the x. That means we want to re-express this region with constant bounds in terms of y and variable bounds in terms of x. And that is going to present a little bit of a challenge to us here because those bounds change. So for example, if we were to draw a little division line here, well, from 0 to 1 in the y-axis, x goes from the first line, which is the line x is equal to y, to the second line, which is the line x is equal to 2y. But above that, from 1 to 2, then x will go from x is equal to y to this line here, which is x is equal to 2. So we need to split up our integral into two pieces. So if we are looking at y values between 0 and 1, if 0 is less than or equal to y is less than or equal to 1, then we're in this part here of the support, and x is going to go. So we're going to integrate from x is equal to y to x is equal to 2y of the density function. So 2/3 xy dx. And this integral is fairly simple to do, so we will anti-differentiate with respect to x. So we get x squared over 2. That cancels out the numerator of 2/3. So 1/3 x squared y from y to 2y, which is going to give us 4/3 y squared y cubed minus 1/3 y cubed, or just y cubed. Now, of course, that's only part of the support. We also need to look at what happens on this upper portion. So if 1 is less than or equal to y is less than or equal to 2, our integral for the marginal function becomes the integral from, well, x is equal to y to x is equal to 2. So from y to 2 of this same 2/3 xy, the joint density function. So we have the same antiderivative, so 1/3 x squared y, but now the bounds are from y to 2, which means that we end up by getting 4/3 y minus 1/3 y cubed. So our marginal function is actually a piecewise function, so we'll describe it in two non-zero pieces. So we've got here the first piece is y cubed, and that is valid when 0 is less than or equal to y is less than or equal to 1. The second piece is our slightly longer 4/3 y minus 1/3 y cubed, and that was valid from 1 is less than or equal to y is less than or equal to 2, and 0 otherwise. So there's the marginal. Now that is going to be the denominator of our conditional density function. So how are we going to find that? Well, we need to split that up into 3 parts as well. So our conditional density function, so f sub x given y is equal to y of x given that y is equal to y is going to be, we'll split that up into 3 parts as well. And the first, right, the numerator was going to stay the same. It's that joint density function for both pieces. So we have 2/3. We'll clean up the algebra in just a second here. We have 2/3 xy, and in the denominator, for the first piece, we're going to have y cubed. And as I say, I will clean up the algebra in just a moment. I'll reduce that fraction. So for that's from 0 is less than or equal to y is less than or equal to 1. The second piece is going to have that same numerator, so 2xy over 3. And then we have this in the denominator, so I'll put that on a common denominator of 3 and multiply by the reciprocal, so that 3 will go upstairs, and then we'll end up with 4y minus y cubed, and that is valid from 1 is less than or equal to y is less than or equal to 2, and again 0 otherwise. So let's clean up those fractions. So the what happens here, those y and y cubed will cancel, leaving me with y squared in the denominator. So 2x over 3y squared, and that is if 0 is less than or equal to y is less than or equal to 1. And then those 3's are going to cancel, and I can factor out a y and cancel as well. So I'm going to have 2x over 4 minus y squared, and that is valid from 1 to 2. And lastly, obviously, we have the 0 everywhere else. So there is the more complicated than in the previous version that we dealt with these two variables. There's the more complicated density function. Now, just as we had before, if we have the density function, then we can use it just like any distribution function, any density. So we can find expected value. Now we're actually given a value for y, so that's fine. We can plug it in and find, right? So we need to integrate to find the expected value. Well, that's going to be the integral from minus infinity to infinity of x times the correct density function, and the direct density function is conditional. So f sub x given that y is equal to 3/2 of x given that y is equal to 3/2 dx. And so what we need to do is here we need to figure out the correct part of the function to plug into. So y is 3/2. If y is 3/2, then that is between 1 and 2. So we're going to plug in here. And so we can plug in y is equal to 3/2. And then we need to figure out the bounds for x, which actually I probably should have done back here. So let's go back and see what we had for the bounds for x. So if y is going from 0 to 1, that's this piece. If y is going from 0 to 1, then x goes from y to 2y, right? So that should have been here as well. Y is less than or equal to x is less than or equal to 2y. And the last piece that we had here, which is actually the piece that we need for part B, if 1 is less than or equal to y is less than or equal to 2, then x goes from y to 2. So x goes from y is less than or equal to x is less than or equal to 2. Good. So now we can plug in our 3/2 here and here to get our bounds, which means that we're going to be integrating from 3/2 to 2, x times, and then we'll plug in y is equal to 3/2 into the density function to get the conditional density that we need. So 2x over 4 minus 3/2 squared dx, and then with a little cleaning up, that is a pretty simple integral to do actually. So let's pull out the constant 2. We'll pull out the denominator. We're going to have 9 over 4 minus, so 16 over 4. And then we're going to integrate from 3/2 to 2. And what's left inside is just x squared dx. So what do we end up by having here? 16 minus 9 is 7. 7 over 4, the 4 comes up. So we get 8/7. And then antiderivative, 1/3 x cubed from 3/2 to 2. From 3/2 to 2, which is going to give us, so 8/21, and we're going to get 2 cubed is 8 minus 3/2 cubed, and if you crunch through those numbers, you will get 37/21.